Today my talk is on the parametric channel estimation for 3D massive MIMO system, and I'll be specifically focusing on millimeter wave communication and how this channel estimation is, this approach of channel estimation is suitable for millimeter wave communication or higher frequency wireless channels. All right, so the outline of my talk is, as a motivation, I will first introduce some key characteristics of millimeter wave communication, and then I will use what is full dimension MIMO or FD-MIMO system, and next I will go through what is the channel estimation approach for our work and the performance characterization, and then I'll go through the Optimum Precoder Design and the power allocation, and finally I'll conclude with some design intuition of our work. Okay, so why millimeter wave communication? So as we know, so day by day our data rate demand is increasing, and in order to cope up with this increased data rate, we have to go through we need higher bandwidth. And the traditional wireless communication, which is like from 300 megahertz to around 2.6 gigahertz. So this is already very crowded. There is not enough space to provide more bandwidth. So one way of increasing this data rate is to go in a higher bandwidth area, like about 30 gigahertz or about 26 gigahertz from 300 gigahertz. So this bandwidth area is called the millimeter wave band. So a great amount of spectrum available for communication purpose, for cellular communication purpose, that we can utilize. So this is kind of one motivation why we should go to a higher frequency communication. All right. So some key characteristics of millimeter wave channel is as follows. So usually, if you look at the microwave cellular system, the number of antennas at the base station is typically 1 to 4, whereas at millimeter wave cellular communication, because of the lower wavelength, we can put now more antennas together at the base station, like 64 to 256. The same can be done at mobile station. So typically at the mobile station is either 1 or 2 antennas at microwave range. But if we use millimeter wave, the number of antennas can be increased from 4 to 6. Now about the channel characteristics, if you look at the lower frequency channel, the number of clusters is typically very high, around 10, 8, 9. So these are the typical number. But if you look at the millimeter wave channel, the higher frequency, then the channel is more sparse. Like the number of clusters in the channel is less than 4. It's like 2, 3. These are the typical number. So another key characteristic is that the delay spread in millimeter wave communication is much less than the traditional low frequency channel. So the now question is, why haven't we been using this millimeter wave channel in the previous years? So previously it was thought that the millimeter wave communication is not suitable for cellular communication. So why? So because of the rain or atmospheric nature. So this communication cannot be done more than a few meters. But some recent channel measurement campaign, we can observe that this is not true. Say, for example, Dr. Ted Rappaport's group has done extensive measurement and showed that there are some range in this millimeter wave communication where the attenuation is very high, but there is also some windows there the attenuation is not that much. So we can still utilize that window, like the green window. And it has been shown that for the cell size of 200 meter, millimeter wave can overcome this rain and atmospheric problem, and cellular communication can still be done. It has been shown that for every kilometer of propagation, only the attenuation is around 7 dB. That's not too much. So these results and this data is taken from Dr. Rappaport's work.
So this 200 meter is considering LOS.
Right, right. Okay. So why massive MIMO? So massive MIMO, as you have already know, I'm pretty sure, is one of the key enabling technology for massive MIMO for 5G system. So what does it provide? So since we have a larger number of antennas at the base station, now we can make our beam narrower. So that gives us the more increased spatial resolution. So we can focus more to a particular user. So that this narrow beam or spatial resolution also translates into a reduced multi-user interference, right? So if your beam is very wide, then if you are trying to beamform towards the user 1, and if user 1 and user 2 are very closely spaced, then that beam can also affect user 2. But if your beam is very narrow, then that beam may not affect user 2. So this increases spatial resolution, also reduces the interference in a sense. And it has been shown that if you are using large number of antennas at the base station, the signal processing can be is very easy. Like we can use simple zero forcing or zero forcing type of simple signal processing at the base station. All right, and why do we need this massive MIMO? Because of the need is higher data rate. We need higher data rate from 3G to 4G to 5G. The data rating requirement is increasing. At the same time, we also need like more uniform quality of experience, right? So QoE. So in order to provide this, the 5G has been looking into this massive MIMO concept very seriously. Okay, so what is the difference between massive MIMO and FD-MIMO? So massive MIMO, if you look at the from theoretical side, they usually don't consider like what is the how. So theoretically they say asymptotically large. So but how large? How can you put together all this large number of antennas at the base station if you are just putting it on the uniform linear array? So there is some base station form factor limitation, right? So you cannot go too large in any particular direction. So FD-MIMO or full dimension MIMO comes into rescue. So they are saying, okay, we are placing a uniform rectangular array at the base station, and so this also not only reduces the form factor issue, but also it can be, since we are placing a two-dimensional array, now we can beamform not only azimuth direction but also in the elevation domain. So because of that, we can now serve a larger number of UVs, like tens of UVs, compared to the traditional beamforming. Okay, so the channel estimation. So why do we need channel estimation? In order to do any kind of communication from transmitter to receiver, the transmitter needs to know the channel. Okay, so this is the closed loop MIMO system. So CSI is very crucial in order to extract all the benefits for FD-MIMO system. It's already very important. It's even more important for massive MIMO or FD-MIMO. And the typical channel estimation approaches are like we can estimate the channel transfer function. Like, so we consider the channel as a matrix, and we try to estimate each of the elements of this matrix. And another way of estimating the channel is to model the channel as a function of some parameters. And if we can know those parameters only, then the whole channel can be reconstructed. So in this work, we adopted the parametric based channel estimation. And so the idea is the base station tries to estimate one parameter, in our case that is direction of arrival. So base station tries to estimate this DOA in the uplink, and assuming that the operation is time division duplex or TDD, then base station can use those estimated parameters for downlink processing. So downlink, for example, downlink precoder design. So that was the main idea. Okay, so what's wrong with channel transfer function based channel estimation? So okay, so estimating the channel transfer function is like is statistical channel model. Number of coefficients need to be estimated goes large with the dimension of the channel. So if the channel is like 2 by 2 or 4 by 2, like 4 antennas at the base station, 2 antennas at the transmitter, that's fine. The matrix is still very small. But if the channel size is like 256 by 2, or like base station number of antennas at the base station is very high, then estimating each of the elements is like extremely complex. The complexity goes larger, and also the energy is not very energy efficient, right? However, if we can model the channel as a function of just a few parameters, and base station can estimate those parameters only, right? Say for example, the channel has 4 paths, and each path has just 4 DOA, right? And say even if it doesn't matter whether the channel is 4 by 2 or 256 by 2, if we know the DOA, you can reconstruct the channel with just 4 parameters, right? Of course, there are channel gains and say DOD. The idea is like the number of parameters to be estimated doesn't increase with the number of how many antennas you are putting at the base station. So that was the main motivation. All right, so the idea is the DOA is very crucial for full dimension MIMO system or massive MIMO system. Okay, so now the system model that we are considering for this work is, so we are placing a uniform linear array at the UE and uniform rectangular array at the base station. At the base station, all the antenna elements are equi-spaced by delta, and the signal is coming from the green direction. So since we are placing a 2-dimensional array at the base station, so the signal will have 2 components of DOA. So one is the elevation angle and another is the azimuth angle. And we pass through it a traditional wave DM modulator, say from IFFT at the cyclic prefix, parallel to serial conversion, and then we convert it and transmit in the air medium. So that was our base station antenna configuration. Now, if you look at the channel impulse response for Lth tap, then we can characterize this channel impulse response as a function of complex channel gain, then receive error response, and transmit error response. So this receive error response is the function of direction of arrivals, and the transmit error response is the function of direction of departure from the mobile station. So now the ERL, which is the receive error response, is actually a vector, and it's a Kronecker product of elevation error response with the azimuth error response, right? So it is a function of both elevation angle and azimuth angle. Now the receive signal, the base station receives the signal and then passes through the OFDM demodulator as a serial to parallel, remove cyclic prefix, and then before applying the FFT, we'll be performing the channel estimation. So we are performing for this work. We are performing channel estimation in time domain. Okay. So any questions up to this point? All right. Okay. So after removing the cyclic prefix in time domain, we can express the receive signal in this form, where the A matrix is the array steering matrix, which is a function of all the direction of arrivals for each of the paths, right? And this B vector or diag B matrix contains the complex channel gain, and this ET tilde or that matrix is the function of direction of departure. and S is the transmitted signal. All right, so our task is to focus on this A matrix because A contains this DOA, and we can feed the rest of, for the channel estimation purpose, we can feed the rest of the part like diag BETS as the equivalent transmit signal, and we'll just focus on the array steering matrix. And as I said, array steering matrix has this as a specific structure. It has the Van der Waals structure. All right. So how do you do the channel estimation? How do we estimate the channel? So, as I said, the array steering matrix, each vector of the array steering matrix has this shift invariance property. So it says, say there are six antenna elements. So if we can form two sub-array within these 6 antenna elements, let's say first 5 and the last 5. So from first 5 to the last 5, there is a fixed phase difference, right? So if we take first 5 and then you multiply constant phase, say to the power j5, you will get the last 5. So this is called the shift invariance property, right? So the array steering matrix A, each column of this matrix has this shift invariance property. So any vector which has this Van der Waals structure will have this shift invariance property. Now we can utilize this shift invariance property of the A matrix or the received signal and apply a traditional well-known direction of variable estimation method called SPIT. In other words, estimation of signal parameters via rotational invariance technique. So as I said, we will focus on A. So we have lumped all the other elements of this matrix and call it equivalent transmit signal. All right. So as I said, the previous one, the example here was for the one-dimensional antenna array, and we can divide it into 2 sub-arrays. Since we are using a two-dimensional antenna array at the base station, we can do the similar sub-array division for the 2-dimensional case. So in the 2-dimensional case, we will have now 4 sub-arrays. So 2 sub-arrays for the azimuth shift invariance, and two other sub-arrays we can form so that the shift invariance in elevation domain is maintained. Okay, and the SPIT algorithm in short is like, first from the received signal, we can estimate the signal subspace, and then we estimate we then form a shift invariance equation, and then solve the shift invariance equation from either least square or total least square type of algorithm. And then we can apply we can extract the singular values or eigenvalues of that shift invariance operator and can extract the DOA information by simple parameter transformation.
So this is irrespective of the size of the rectangular?
No, actually it depends on the, as long as you are using a rectangular array, uniform rectangular array or uniform linear array, you are in good shape. But if you are using some random antenna array, there is no particular structure from one antenna element to another antenna element, you cannot use SPIT type of algorithm. So SPIT requires you to have shift invariance, right? So from the phase difference from antenna 1 to antenna 2 should be the same as the phase difference from antenna 2 to antenna 3. So as long as you can find any antenna array that holds this property, you can apply this kind of techniques. Any other question? All right. Okay, so skipping all the details, let's just focus on the some results. So we characterize what is the performance of DOA estimation, like in terms of root mean square of the estimation of the estimation error. So as you can see, our this performance characterization depends on a few physical parameters. For example, the number of antenna placed at the base station, number of snapshots taken from the received signal, and the covariance matrix of the equivalent transmit signal, and and the SNR, and that's it. So, and another interesting thing is, so this performance RMSE depends on a specific structure of the antenna array. So one antenna array, if you are putting the 4x16, and if you are putting a 16 by R, say 8 by 8, the performance may be different, right? Because say if you look at the M1 minus M1 minus 1 square M2, where M1 and M2 are the antenna element placed in the elevation and horizontal domain respectively. So we can. So the idea is number of base station antennas and the structure of the antenna array actually affects the DO estimation performance.
So there is always an optimal antenna pattern, like 8 plus 8 or 4 plus 6 grades and 20 grade. One of these two elements will perform better.
Yeah, the key idea is like if you are the conventional notion is if you are putting more antenna elements in a particular direction, you are expected to get better result, better estimation in that direction, right? So, but some of our results show that it may not be true. Say if you are putting 4x16 antenna array, right? So 16 antenna elements in the azimuth domain. So you are expecting, you should expect better resolution in the azimuth domain than 8 by 8, which has only 8 antenna elements at the azimuth. So some of our results show that this may not be true, because the azimuth estimation performance is actually coupled with the elevation estimation performance. If you look at the elevation, elevation characterization is not dependent on azimuth, but azimuth characterization is dependent on elevation characterization. So in some cases, your elevation is, if you're so poor, then that affects the azimuth. So even though you are putting 16 antenna elements in the azimuth, the performance may not be as good as 8 by 8, right? So 4 by 16, that means there are just only 4 antenna at the elevation and 16 antenna element and the azimuth. So that 4 antenna is making the elevation performance bad, and that may affect the azimuth. So there are some intuition here. Yeah.
So typically the elevation is somewhat limited in range with respect to the azimuth typically goes from -60 to +60, whereas elevation is
correct.
Somewhat restricted between say 2 degrees and.
No, it depends on how you compute the angle. Say, yes, 75 to 90 degree.
Yeah.
Yeah.
So in that range, is it possible to say which one dominates the performance and which one doesn't? Elevation versus azimuth.
Which one dominates the performance?
Mean square error.
So mean square error of elevation, or?
Yeah. Because elevation is somewhat restricted in a small range of values.
Right. So which one dominates of 8 by 8 dominates of?
Yeah.
So for this work, so let me explain. So you are saying if you restrict the elevation angles in a very smaller range, whether it affects, then it's like a larger range from 180 to 80.
So
yes. So say if you are taken from a larger antenna array, and if you are say larger angle range, or if you are taken from a smaller angle range, the performance will vary. Okay, but our resolution of estimation is like on the level of the high. If you look at the high SNR range, on the level of 0.1. Right? So if you have 4 or 5 paths within 2 degree, say within 2 degree, if you have 4 paths in the channel, then of course that will affect elevation. Right? Yes.
But does it mean that we need more resolution in the elevations? Where I was speaking.
I think you raised a very good point, saying that because for elevation domain we don't have so many degrees of freedom.
Right.
We only have 15 degrees, and on the azimuth we have 120 degrees, right? And probably it's better for us to do, let's say, which, let's say, direction is more important, right? That's your question. Your question is good in the sense of if you look at traditional communication systems, cellular systems. So you have a cell tower of 35 meters, and then you have cell range around the kilometers, 500 meters per kilometer, and then you assume use a uniform distributing the area that is around 15 degrees. However, you know, the recent trend is that we are talking about small cells. But we're talking about like high buildings. I mean, even in Ruby as well as the picture, it shows actually tall building, right? And then that opens up a lot of degrees of freedom in the elevation domain. So we are not only restricted to, so now the user is not 2D anymore. So cellular network is not 2D anymore, it's 3D. Okay? And then that means that we have more degrees of freedom in the elevation domain. And how elevation estimate and azimuth estimate, how that impacts the overall performance metric, which is throughput, I think we are going to discuss about this later.
Right.
And so out of the day, DOM estimation is a byproduct. It's an intermediate product. It's not the final product. We talk to communication people and say, hey, the DOM estimation error is error 10 to minus 3. What is that? I don't care. Right? What I care is about finally what is the throughput, what is the actual achievable rate, what is the probability, various things like that. So he's going to, I think you are going to relate that to the throughput, right?
Right.
But the key side here is that, I mean, traditionally, I think 5 years ago, 6 years, around 6 years, 5 to 6 years ago, we worked with Center Research. They have this problem. They think about two-dimensional antenna. Already have 64 antenna elements in front of them. They are saying that, how should I put this 64 elements? I should put it in 2 by 32, 4 by 16, 8 by 8. I mean, there are so many ways to put it. And then they asked actually Center Research, my former colleagues there, they asked them, what is the best way? Because they think in the same way, azimuth is more important. And they're saying that, hey, what is the best? I want to have a final resolution with azimuth. So they're saying that if I can put 1 by 64, that's the best. Okay? And actually, our result telling them, no, that's not the case. Okay? Overall, probably it's not a good idea to put 1 by 64, even 2 by 32, even 4 by 16, because elevation and azimuth are coupled, running in the 3D world, they're not in a separate world. So everything's coupled. That's why actually this result is showing you. In fact, our first solution result shows them actually 8 by 8 performs better than 4 by 16 in terms of elevation. Azimuth, in certain scenarios, they were thinking this is wrong. I think that go back to the simulation again, verify this is correct. Okay, and then we analytically showed it, and then show actually, well, yeah, in some cases we are right. So 8 by 8 sometimes performs better. Does that make sense?
Okay, so some simulation results. We assume this is the far field assumption, like plane wave is impinging at the antenna array, and isotropic and linear transmission medium. So as you can see, as the SNR increases, our estimation performance also increases, like on the 0.1 degree level. And as SNR increases, our simulation results also matches the analytical results pretty closely. All right, so these are the other results for 4 by 16 and 16 by 16. So as you can see, as the number of antenna increases, the estimation performance also increases. Like for the 16 by 16, there are total 256 antenna elements. So the performance is now almost 0.02 level, whereas for the 8 by 8, it was around 0.01 level. All right, so this was the so this is the we can show how for the rectangular array, like the same number of antenna at the elevation and azimuth, we showed how we increase the number of antennas, how the performance is increasing. So we have plotted for different distribution of angles. As you can see, our simulation results and analytical results matches very closely. And as the number of antenna increases from 6 by 6 to 16 by 16, the performance momentarily gets better and better. Okay, so this was the part of the channel estimation characterization. So any other questions about from estimation part? No. Okay, good. So in this part, I'll just connect how this DOA estimation affects the achievable rate, precoder design, power allocation, and that kind of things. So the idea was that we estimated the channel in the uplink, and we are assuming the channel is mode of operation is time division duplex. So we can whatever we estimate in the uplink, we can utilize in downlink. Okay, so in the downlink we can write the channel equation in the downlink form, in ADB form, where A is in the uplink we can write it in the ADB form, where A is the steering matrix, D contains the complex channel gain, and B contains the direction of departure. So the downlink channel will be just a transpose of the uplink channel, so we can write it in BDA form. Okay, so whatever we estimated in the uplink in say DOA in A, so those will be the same DOA for the downlink A, right? The same steering matrix.
Just a small mistake, not that directly related. So this to exploit this TDD thing, we need to make sure that the reciprocity calibration is
right.
good.
Correct.
So how difficult or easy it is in the millimeter wave and the microwave?
I think it is more it is less difficult in the millimeter wave because there are less number of parameters, right? And another thing is even if you are not perfectly calibrated, say, but so you are saying if you are not perfectly TDD, the channel is not, you want to operate in the FDD mode. So these DOA and the delay parameters, or DOD, so these are relatively long-term statistics, right? So even if we're using FDD mode, you can still utilize this DOA information or parameters estimated in the uplink for downlink beamforming. So they don't change quite often. So if you are, say, from perspective of synchronization, so say you estimated once and it took a longer time to estimate those DOA. So you can still use those estimated DOA or estimated parameters for downlink for say 30 or 35 symbols, because they are not changing that fast. Does it make sense? Okay. All right, so the capacity, the mutual information can be written in terms of the downlink channel, and the corresponding system capacity can also be characterized. Let us now consider this lemma. So this lemma says, as long as we pick the DOAs from any continuous distribution, so the two steering vector in the array steering matrix will be orthogonal. Orthogonal in asymptote when the number of antennas at the base station goes large. So this is a very kind of now is already established result. So we will be utilizing this result in our achievable rate performance. So using the previous lemma, we can show that the optimum downlink precoder is given by the first equation. So as you can see, this downlink precoder is a function of the steering vector. In other words, the optimum downlink precoder is the function of the DOA that we estimated in the uplink. So it says if we know the DOA, we can form the perfect precoder, optimum precoder. Okay. So and accordingly, if there is no say channel estimation error, say we estimated the channel perfectly, then the power allocation will be the conventional water filling algorithm. All right. So now what if there is channel estimation error, and how does it affect the achievable rate and power allocation? So of course there will be channel estimation error, right? We characterize the estimation error, previous one. So we will see how that estimation error affects the power allocation. All right. So if there is estimation error, then the mutual information can be characterized by the first and second equation, right? And now if you look at the expected transmit power, so that is not a straightforward water filling algorithm. So the final equation shows if we consider the estimation error in the uplink, the water filling, the optimum power allocation is given by this equation. This is a function of delta VL and delta UL, that is estimation error, right? So it is not completely, it is not a completely water filling, but it's a modified water filling. So if you plug delta V and delta U as a 0, that is the perfect channel estimation case, then this will reduce to, again, the conventional water filling. Okay, so I think so this is where we relate the estimation error with the achievable rate and optimum power allocation. All right, so this is the result. So previously we all talked about the only one parameter estimation, the DOA. So here I just briefly mentioned, I'll not go into details, what is some benefits of joint parameter estimation. So some of the benefits of joint parameter estimation is we can have better accuracy in the, estimation performance, and we can now estimate more resolvable paths than previously done. Even if the number of antennas at the base station is lower than the number of paths present in the channel, we can still form some modified steering metrics that will help us to estimate those higher number of paths, higher number of resolvable paths. Okay, so I just put some expression or analytical expression for the joint angle and delay estimation. So as you can see, so this result is slightly different from this result is from a slightly different system model, but we can still get the intuition here. So if you remember previously in the denominator, there were just M and N, right? There are just antenna elements. So if you see the number of antenna elements increases, the estimation performance also increases. So now here is some one extra term K, which is the how many symbols you are using in order to constructing that array manifold matrix. So this says if you increase the number of symbols in constructing the array manifold matrix, then you can still get the same level of accuracy, estimation accuracy, with lower number of base station antennas. Okay. So the simulation results and analytical results also show that if you estimate the separate, the black one, the estimation performance is much worse than the estimation if you just estimate the if we estimate both angles and DOA separately. So this result is for the delay estimation. So all the details of this work can be found in the reference. If you're more interested, you can go through. I think this was my the second to last slide. So in this work, we have we just highlighted some potential benefits of millimeter wave communication for 5G system, and we highlighted why it is very essential to find out a robust channel estimation technique for millimeter wave system. An accurate CSI is very critical for massive MIMO. In this work, we have formed a DOA-based channel estimation method, and we analytically characterize the estimation performance. We related how this achievable rate and power allocation is connected to the estimation error. And our results show that the RMSE depends on the number of antenna at the base station, transmit signal power, transmit covariance metrics. And of course, antenna configuration at the base station also plays a key role in determining the performance of estimation. And finally, we just looked over some ideas on how joint parameter estimation can be more beneficial than the separate parameter estimation. All right, so this was it. So if you have any question, please feel free.